Alright, so today we're going to be looking at our work and energy review, going through each problem, just walking you through step by step how to solve them. So let's take a look at number 1. A gardener lifts a 2.5 kilogram bag of sand to a height of 1.1 meters, carries it around the yard a distance of 1.5 meters at a constant speed and height, and sets it down back on the ground. Part A, what is the change in potential energy when the gardener lifts the bag of sand? So here, we want to look at exactly what is happening. I always like drawing out a picture, so let's just start with that. We have some flat ground, maybe we have our gardener right here, and they are picking up and lifting a bag of sand. They're lifting it to a height of 1.1 meters. So it starts on the ground, then they lift it up into the air. So if we say maybe this is our bag of sand, they lift it up into the air, where it's now in their arms. This height is 1.1 meters that it gets lifted. What is the change in potential energy? Specifically, that is gravitational potential energy. Since it's gaining height when the gardener lifts the bag of sand, well, we can just use our equation. GPE equals mgh. Plug in what we know. The mass is 2.5 kilograms. G is 9.8. And our height is 1.1 meters. So that means if we go ahead and we multiply, let's grab our calculator out. There we go. We are doing 2.5 times 9.8, and we're multiplying that by 1.1. So this gives us an answer of 26.95 joules. Now the unit on that is joules because of course it is an energy, so energy is always joules. Part B, how much work does the gardener do when he lifts the sand? So now we're asking for work. We have two different equations for work. We have work is equal to a force times the distance, and we have work is equal to a change in energy. You can use these interchangeably. They both give you the work, but it's obviously easier to use the one that you have the variables for. So what we're going to start out with is just identifying, what do we know? Well, we know it went from 0 gravitational potential energy at the ground to 26.95 joules of gravitational potential energy when the gardener lifts it up. So the change in energy there, with our equation, work is equal to our change. In our equation, it just says change in E for energy. I'm going to say that's the change in our total mechanical energy is our work. We can always find this as taking the change in anything is just the final minus the initial. Change in velocity, that's the final velocity minus the initial velocity. Change in total mechanical energy, that's the final total mechanical energy minus the initial. And here, we started off with 0 joules of energy, no gravitational potential energy, no elastic potential energy, no kinetic. And then our final energy is just our 26.95 that we get from part A. Subtract our 0, our change in total mechanical energy is just that same 26.95 joules. So the work done is that change in energy. Our work is 26.95 joules. Okay. Part C. How much work does the gardener do when he carries the sand across the yard? Okay. So our worker, they carry it all the way across the yard, still in their hand. This is along the same height. If we draw in kind of a level right here, we can say the height of that bag of sand is not changing. So the gravitational potential energy is not changing. They are carrying it around at a constant speed. So that means that there is no change in energy. It's not gaining height. It's not gaining kinetic energy, so there's no change in energy as they're carrying it across the yard. So the work done here is 0. You can also take a look at your work is equal to force times distance equation and say, well, aren't they applying some force over some distance? Well, if we look at our picture, to keep that bag of sand in the air, the person is applying an upward force on it as they walk across. Upward force on the bag of sand, while the distance they are moving is to the right. Since the force is perpendicular to the distance, that force is going to do no work. The force only does work when it is parallel, so either in the same direction as or in the opposite direction as the force. So we do 0 joules of work. How much work does the gardener do when he sets the sand back on the ground? Well, let's use our same process from part B. We'll use our same equation. We will say, okay, that our change in total mechanical energy is just the energy that the bag has in the end, the final total mechanical energy minus the initial total mechanical energy. The initial total mechanical energy is just our same GPE from part A, since it's in the air at that height. We'll plug that in, 26.95. And our final total mechanical energy is, well, it's on the ground at rest, so it has no energy. If we do our math, 0 minus 26.95 just gives us negative 26.95. This is, of course, in joules. Since work is equal to our change in total mechanical energy, the work done is equal to negative 26.95 joules. That being a negative means that, of course, the energy has decreased, and that makes sense, since it was at some height having some gravitational potential, and now it is on the ground, it lost that gravitational potential energy. Okay, let's keep going. Hockey player pushes a 0.25 kilogram hockey puck over frictionless ice with a constant force, causing it to, let's check it out, causing it to accelerate at 24 meters per second squared over a distance of 0.5 meters. Calculate the force the hockey player exerted on the puck. Okay, so here, we want to pull out everything that we have, right? We have the mass of the hockey puck. We can say, okay, the mass, 0.25 kilograms. We get 24 meters per second squared. That's an acceleration. We can tell that it tells us that it's accelerating. And the units, meters per second squared, those are units of acceleration. Let's write that down as well. Let's also pull out our distance of 5 meters. 0.5 meters, that is. We have our givens written down. Now let's look at our problem. Calculate the force the hockey player exerted on the puck. Okay, well, force exerted. We have to think back to our forces unit. This isn't an equation on our equation sheet, but we know that the total force, also sometimes referred to as the net force, is equal to the mass times the acceleration of an object. Well, we have the mass, and we have the accelerations. Let's go ahead and plug in our mass, 0.25. The acceleration is 24. We get our total, just 0.25 times 24. That is going to give us a total force, or net force, of 6 newtons. So we've calculated the force the hockey player exerted on the puck. It is 6 newtons. Part B, calculate the work done by the hockey player on the puck. Use your answer to part A. Well, work, we have 2 equations, right? We have work is equal to the change in total mechanical energy, and we have that work is equal to the force times the distance. How do I decide what equation to use? Well, let's look at what we're given. Work being a change in total mechanical energy. If we had information about maybe how fast the hockey puck ends up at, we could calculate that final kinetic energy and determine how much it changed its energy. But since we don't have that information, our best bet is using our second equation. Work is equal to the force times the distance. So we'll use that. We'll say, okay, the work done is equal to the force, which we just calculated. It's that 6 newtons, times the distance. The distance is 0.5. Just taking it from our givens, multiply these together, we get our work as 3 joules. Now, that's our answer for part B. Part C, calculate the change in kinetic energy of the puck. We're using our answer to part B. We're going to use our definition of work as a change in total mechanical energy. We just copy this equation, put it down here. Work is the change in total mechanical energy. So if our work is 3 joules, right here, then we're saying that the change in total mechanical energy is 3 joules. The hockey puck, it's not gaining any height, it's not heating up, so that work must all go into the kinetic energy, and the puck is gaining 3 joules of kinetic energy. So that change in your kinetic energy is going to be 3 joules. All right, let's take a look at the second page. Number 3, which has more kinetic energy when it hits the floor, a cork sphere dropped from 2 meters or a lead sphere dropped from 2 meters? Well, to do this, we're being asked about the kinetic energy when it hits the floor. Let's take a look at our kinetic energy equation. We have mass and velocity in there. So how do we determine which is going to have more kinetic energy? Well, we can use our law of conservation of energy and say, let's draw a situation. We'll have our cork right here, and then we will have lead right here. And if they are falling onto the same ground 2 meters below, which one will have the greater kinetic energy? Well, we just have to identify the types of energy that are going to be present. At the top, for both the cork and the lead sphere, we will have gravitational potential energy. And then, for both the cork and the lead sphere, we will have kinetic energy at the bottom. So we are saying that the total mechanical energy at situation A, where it is at the top, is going to equal the total mechanical energy at the bottom. So that is going to be our initial situation. They just have their gravitational potential energy at the top. It's going to turn into kinetic energy at the bottom. But how do these energies compare? For this, we really want to look at our gravitational potential energy equation. Gravitational potential energy, that is just mgh. Well, what's different between our cork and lead sphere? They have the same g value, that acceleration due to gravity. They're on the same planet, so that stays the same. They're both 2 meters above the ground, so our height stays the same. What's changing is the mass. The cork has less mass than the lead. So, for the lead having more mass, that also means it will have more gravitational potential energy. Since the lead sphere will have a greater gravitational potential energy to start, it will have a greater kinetic energy at the end. So, all that to say, the lead will have a greater kinetic energy. Number 4, to get the ball to move faster, do you drop the ball from a higher or lower height? Well, you're going to drop it from a higher height. Sometimes we get tripped up on ourselves in physics, because if we asked you this question before you even set foot in a physics classroom, all of you would say, oh, to get the ball to go faster, drop it from a higher height. You can always take a step back, especially during multiple choice. Think through the situations. What do you expect? What do you know to happen? And then double check with your physics. Here, our instinct, we say, oh, drop it from a higher height. That's going to make it go faster. Why does it make it go faster? Is just what we said for number 3, is we're saying, well, at the very top, where we have, let's bring this over, at the very top at situation A, we have all our energy in gravitational potential energy. In a situation like this, in situation B, we have all our energy in kinetic energy. So whatever energy you start with, gravitational potential energy, it's going to turn into that kinetic energy. So if you lift up, go higher in our gravitational potential energy equation right here, the height is a factor in our gravitational potential energy. So as you take the object higher and higher off the ground, it will have a greater gravitational potential energy. And thus, when that greater gravitational potential energy turns into kinetic, it will also have a greater kinetic energy. And since the mass of the object is staying the same, that won't be a factor. The velocity will increase when you drop the object from a higher height, because it will have more gravitational potential energy, and that will turn into more kinetic energy. What is the advantage of using a ramp? Look at the packet's last page. So on the packet's last page, page 19, we have a problem that looks a little something like this. We have a triangular ramp right here. Someone is taking the box, lifting it up from the ground up to the tippy top. They're lifting it vertically like this, 3 meters, while another person is taking that same box and starting at the ground, they are pushing it to the top. And they are pushing it along this distance, which is 4 meters. So here, we are saying that both objects reach the same height. Both the boxes, they start with 0 joules of energy at the very bottom. They end up with some amount of gravitational potential energy at the top. They're the same box, so they end up with the same gravitational potential energy at the top. They have the same mass, same g value, same height, same GBE. So, since they change their energy the same amount, we say that the work done is the same. So here, they have the same work because both boxes increased their energy by the same amount. They both gained the same amount of gravitational potential energy. What's different is that if we look at our work equation for force times distance, we say work is equal to a force times a distance. Well, the person that is moving it vertically, right here, they are moving at a distance of 3 meters, while the person pushing up the ramp is moving a distance of 4 meters. If we break down what that happens with our equation, is if we have the same work being done, which we do. Here, this is the same work being done. The person pushing it vertically upwards 3 meters, they will apply a bigger force over a smaller distance, while the person applying the force over a greater distance will apply a smaller force over a larger distance. And if we think about what's easier for us humans to do, well, it's easier for us to apply a lower force for a longer time than a really heavy force. For example, if you're trying to push something super heavy, bring it to some shelf, it's a lot easier if you can push it up a ramp. Maybe you can generate enough force to actually push it up a ramp, whereas you wouldn't be able to just pick it up and lift it straight up. It's the same work done in either way. It's just that increasing the distance you are doing that work over makes it so that when you're doing the same amount of work, increasing the distance decreases that force for the same amount of work. How do you do negative work on an object? Well, there's a ton of different examples. You could talk about, say, if we draw in some grass and we have maybe a soccer ball rolling in that grass. The soccer ball is rolling to the right. This is our distance. It's moving to the right. But the force on the soccer ball is to the left. Since the force is opposite the direction, that does negative work. The soccer ball loses energy as it slows down. We're talking about a person actually doing negative work on an object. There's a couple examples. Generally, it is involved in slowing an object down or bringing an object down from a height. So for example, let's say you are hungry for some chips, and you have chips up on top of the top shelf in your cabinet. If here are your chips, they have some amount of gravitational potential energy. You grab the chips, and you bring them down to some lower height. The chips had a lot of gravitational potential energy, and then now they have less gravitational potential energy because you brought them down. As you're bringing the chips down, your force is upward, but the distance the object traveled was downward. Another similar example to that is if you are, say, working out and you are doing maybe a shoulder press, something where you have a big weight above your head. Let's draw our big weight. Maybe this is our barbell. It has gravitational potential energy. A few seconds later, you bring it down to, say, about your chin. The weight has lost energy because you did negative work on the object. As you bring the weight downward, you are still applying a force upward as it is moving down. Because those are in the opposite direction, that does negative work. The energy in the system has decreased. And that's the key to identify if negative work is done, is if the system decreases energy, you know negative work was done. Let's look at number 7. 0.3 kilogram T-ball is sitting at rest on a tee. The batter hits the ball and it flies into the outfield with a launch speed of 19.2 meters per second. Calculate the work done in hitting the T-ball. Consider the kinetic energy before and after the ball is hit. Okay, so we have a little hint there. What we want to do is we have our equation for work being that change in total mechanical energy. We'd love to use our work is equal to a force times a distance equation, but if we look at what we're given, we have no force, we have no distance, so we don't have a hope of using that equation. We have to use our work is equal to a change in energy equation. To do that, like we said earlier, the change in total mechanical energy, it is always going to be your final total mechanical energy minus your initial total mechanical energy. Here, let's identify the types of energy. We are saying the batter hits the ball, it is sitting at rest. So initially, sitting at rest on a tee, it has no energy. Or rather, let's draw this out. Let's say we have the ball on a tee right here. Maybe this is the ball. Sitting on a tee. It is hit, it flies into the air. Our two situations, the final and the initial, are going to be at the same height. The initial situation is before the ball is launched. The final situation is right after it gets hit, but before it's gained any height. So really, the gravitational potential energy is going to be the same for each situation. So that doesn't get factored into our change. It's not changing at all, so it isn't factored into our change in energy. The type of energy that is changing is the kinetic energy. And we're saying that initially, that ball is sitting at rest on a tee, so its initial energy is 0. The final energy is just going to be whatever the kinetic energy is of the object right after it's launched. We can find that using our equation for kinetic energy. We can say our final kinetic energy is just going to be 1/2 the mass times our final velocity squared. And now, we're using this final term in kind of a relative context. We're saying this isn't really the very final speed of the object, but it's going to be after the collision. So here, we're using this initial speed for our kinetic energy right after we collide. So let's plug that in. If we go ahead, we can get our calculator. We're going to plug in 1/2 times the mass, 0.3, times our velocity, which is 19.2 squared. Grab our calculator, let's see if I can. So we are doing, always want to square first. So 19.2, we're going to square that. That's not a square, that's the inverse. Definitely don't want to do that. So we square the velocity. That's the only thing being squared. Then let's multiply by our 0.3. Multiplying by 1/2. And we get the kinetic energy, 55.3. We'll round it to joules. What we're saying is that is the energy that the baseball has gained right after it's hit. So right after it's hit, that's how much kinetic energy the object has. Okay. Now, for part B, we get our kinetic energy. That is going to be the work. Because if we look back over, we plug this in to our kinetic energy. That is how much energy the system gained. It started with no energy. We end up with 55.3. So our change in energy for this equation is our 55.3. So we can say work is just however much kinetic energy was gained. Part B, the ball reaches a maximum height of 12 meters. Calculate the velocity of the ball at this height. Okay, so this is going to be a conservation of energy. We are going to say, and here we didn't specify this, but we are going to say that the ball is starting at a height of 0, and it reaches a maximum height of 12 meters. So what we can do is, in our image, we can say, okay, maybe this is some amount of height off the ground. It reaches some maximum height, 12 meters. But we're going to, again, ignore that at the very beginning. Say it's just on the ground. It's going up to 12 meters high. Calculate the velocity of the ball at this height. We're going to use our conservation of energy. Right? There's no more work being done. So the energy must be conserved in the system. At situation A, that's right after it's hit. Situation B, that's at the peak in the height. So we can identify our types of energy. It is on the ground in situation A, but it's moving, so it has kinetic energy. Situation B, it is moving to the right, and it's above the ground, so it has GPE as well. So in situation A, we'll just say it has its kinetic energy. Situation B has its kinetic energy and the gravitational potential energy. We can do now, substitute in our equations. So kinetic energy is 1/2 mv squared. Do that again for our other side. GPE, that's mgh. Now we just have to plug in everything we know. We actually calculated the kinetic energy of the ball at point A. We have the numbers. We can do that calculation again. If we go ahead, we grab this, we can bring it on over. And we're just going to go ahead and start. So, right here, 1/2. The mass is 0.3. That velocity is what we had before, that initial speed 19.2. We're squaring it, is equal to 1/2. The mass doesn't change, but our velocity, that's what we're solving for. mgh, 0.3 for m, 9.8 for g, and that height given to us as 12, saving room by just not putting in my units there, just for the sake of saving a bit of room. If we go through, we can do all of this calculation, and it is a bit of a big calculation here. Again, our focus is always on the physics, not necessarily on the algebra, so don't fret if you're not incredibly confident on solving from here, because you will get most of your points if you just show your work, but we want all our points. So let's show how to do this calculation. We want to isolate our variable right here, the velocity at b squared. So what we're going to start off with, I'm going to solve for our first term on the right. So there we go. Okay. So we will do, again, 19.2 squared multiplied by 0.3 multiplied by 0.5. And we already did this calculation in the previous problem, but just wanted to show where it's coming from. You can do it again, but if you recognize that it's the same kinetic energy you just calculated, feel free to just take that and set it equal in our equation. We are going to then say this is equal to our 1/2 times 0.3. That gives us a 0.15. The velocity at b squared comes along, And now we want to take 12, multiply by 9.8, and multiply by 0.3. We get our 35.28. Let's round that to just 35.3. Now we want to go ahead. We will subtract 35.3 from both sides. This is going to give us, if we move it on over, it's going to give us 20 is equal to 0.15 velocity at b squared. Now we divide both sides by 0.15. That cancels. And we get 20 divided by 0.15 equals 133. If we keep bringing this over, now we have 133.3 is equal to the velocity at b squared. Take our square root. All right, square root of our answer is 11.5. So the velocity at point B, 11.5 meters per second. Number 8. An arrow with a mass of 0.32 kilograms is shot straight up into the air, reaches a height of 150 meters before stopping and falling back to the ground. The arrow was not shot from the ground. Just after launch, the arrow had a height of 1.8 meters. Calculate the initial velocity of the arrow. Okay, so let's go through. Let's draw this out. So we are saying we have some ground right here. Maybe we have a person, and they are launching an arrow. Let's do our best to draw a little bow. They're launching an arrow, and it is going to be moving straight up. The arrow is not shot from the ground. We say the arrow has a mass of 0.32 kilograms. We also say that it reaches a height of 150 meters, so it's going way, way, way up into the air. Here is the very top. This height is 150 meters. It stops at the top and falls back to the ground. The arrow was not shot from the ground. Just after launch, the arrow had a height of 1.8 meters. So just after it's launched, right here, this is 1.8 meters. Now this, of course, is not drawn to scale, but we're going to do the best we can. Calculate the initial velocity of the arrow. Well, here, no work is being done. The arrow is released, energy is transferred, but doesn't leave our system. We're going to be able to use conservation of energy. We can just say total mechanical energy at A is equal to the total mechanical energy at B. So, at A, that will be right after it's launched. B will be the very top. At situation A, we have some gravitational potential energy because it is off the ground. We also have some kinetic energy because it has been launched and is moving. At situation B, at the very top, we have our gravitational potential energy. And now a key step here is it is shot straight up. So we know at the very top, it is not moving. It's not moving left, not moving right, not moving up, not moving down. It has a velocity of 0 at the very top, so it doesn't have a kinetic energy. Now we'll continue on. We'll plug in our equations, replace MGH with, or replace GPE with MGH, KE with 1/2 mv squared, and now we can plug in everything we know. The mass, 0.32. G of 9.8. The height initially at A is that 1.8. And we're saying 1/2 the mass. It's still our 0.32. This is the velocity that we are solving for. The initial velocity, the velocity at point A. Plug in our mass. Plug in our 9.8. Plug in our height. This is our maximum height now. So that is 150. This time. Again, we just have to solve this just like we did before, but let's go ahead and show that with our calculator. We are saying we're going to start off with 0.32 times 9.8 times 1.8. This is giving us 5.64. We'll round to the second decimal this time. 1/2 of 0.36, 0.32 rather, is 0.16. We have to bring along our velocity, our unknown, what we're solving for. And then we'll say 0.32 times 9.8 times 150 is equal to, let's get that in a fraction. Wrong function. Let's get that in a decimal. There we go. 470.4. Now we just want to go ahead and subtract our 5.64 from both sides. This is going to cancel. We'll take our answer, subtract that 5.64. Now we get 464.74 is equal to 0.16 velocity squared. Now we just want to go ahead and divide by our 0.16. That cancels it. And now we get the velocity squared is equal to 2,904.75. Last step, take our square root, and we get the velocity. Find out that it was 53.9 meters per second. We can even say that this velocity is upward, but we already had it as positive. All right, fill in the charts below. All right, let's look at page 3, number 9. Fill in the charts below. Water balloon is stretched. Water balloon in a stretched slingshot, 1.2 meters above the ground at the start. Let's take a look. So, at the start, before release, it is not on the ground. We know it is 1.2 meters above the ground. Remember, if we're just identifying energies, we have our questions we can fall back on. For gravitational potential energy, ask, is it at a height? Is it on a hill? Is it above the ground? That gives you gravitational potential energy. So here, we are above the ground. Let's give some amount of gravitational potential energy. Maybe I'll even try to color code. We'll say we have GPE. Some amount, 1.2 meters off the ground. Maybe we can do 4 boxes worth. Then, kinetic energy. Well, is it moving? No. So there's no kinetic energy. Elastic potential energy is something stretched or compressed. Yes, absolutely. Let's do a lot of elastic potential energy. That slingshot looks like it's pulled back pretty far. So maybe we'll do, if we did 4 GPE, let's do 8 EP. This brings our total to 12. There is no work being done here. So our total should always be 12. We're going to keep that total of 12 as we're going through. Immediately after released, we were saying there is no height gained and the slingshot is no longer stretched. When the slingshot is no longer stretched, we should have no elastic potential energy. If there's no height gained, we should have the same amount of gravitational potential energy. So let's put that in. We still have our 4 bars gravitational potential energy. But if our total is supposed to be 12, where did that elastic potential energy go? Well, it turned into kinetic. It's the only place it could go, since our gravitational potential energy is not increasing. So let's fill in. That elastic potential energy just turned into kinetic. It's just like our Nerf launcher lab. We have gravitational potential energy. The elastic turns into kinetic. The balloon is at the top of its arc. Is the balloon still moving? Yes, it is at the top of an arc. So here, it's not launched straight up. It is launched, follows a trajectory, something like this. So right at the peak, it is not moving up and down, but it is moving to the right. So it is moving. At the top of the arc, again, slingshot no longer stretched, no elastic potential energy, but our height has increased, so we should have more GPE. but it's not entirely going to be GPE because, like we said, we're still moving. So let's say we have a little bit of kinetic energy. Maybe we have 2 bars of kinetic energy, some amount of kinetic at the top. Then our total is still 12. So that means we need 10 boxes of gravitational potential energy. Let's fill that all in. Okay, there we go. Energy is conserved, its total is staying the same. Let's look at our final situation just before hitting the ground. No more height. Okay, so now we've reached our highest point, we're on the way down. We are actually right about to hit the ground. We are flying through the air really fast all the way at the ground. So there's no longer GPE since we're at the ground, no more height, there's no elastic potential energy. All of its energy must be kinetic. So we go ahead and we said, well, we have 12 total energy. So if all our energy is kinetic, we must have 12 kinetic. All right. A reminder that the bar charts, they're not for an exact distribution of our energy. It's just to kind of represent where is our energy in the system. All right. Number 10, the slingshot above can store 0.05 joules of elastic potential energy when pulled to its maximum stretch. How much KE will a 15-gram water balloon have the instant it is released from the slingshot? Okay, well, let's look at our bar chart. We are saying we have some amount of elastic potential energy right here. If this is 0.05 joules, that energy turns into kinetic energy right here. The gravitational potential doesn't stay the same. The total is still 12 boxes. So our kinetic energy must be that 0.05 joules as well, because everything stored in the slingshot didn't go into gravitational, it all went into kinetic. So it will have 0.05 joules of kinetic energy right when it's released. Now, how much K will a 30-gram water balloon have? Since the slingshot is stretched to the same amount and the energy is stored in the slingshot, it doesn't actually matter how many grams the water balloon is. It's going to give that same amount of kinetic energy. If we think back to our Nerf launcher lab, we had our heavy dart and our light dart. The elastic potential energy stored in the Nerf launcher was the same for both of them. So when we fire our Nerf launchers, that elastic potential energy turns into kinetic. So for both the light and heavy dart, they have the same kinetic energy. But also pulling from our Nerf launcher experiment, which water balloon will leave the slingshot at a greater velocity? We know the lighter one, the 15-gram, will leave with a greater velocity. Now this is due to the energy. We say, well, if they have the same kinetic energy doesn't just depend on velocity. So, if we look at our equation, we can split it up 2 ways. For the same kinetic energy, we can have that kinetic energy where the object has a really tiny mass and a large velocity. Or they can have a big mass and a small velocity, both giving the same kinetic energy. So, since the objects have the same kinetic energy, whichever one has the smaller mass, just like our lighter Nerf dart had the smaller mass and the greater velocity, the lower mass water balloon will leave with a greater velocity, since the same amount of energy is stored in that slingshot. Alright, let's look at our final page of the review. Number 11, Charlotte can consistently throw a 0.2 kilogram ball at a speed of 12 meters per second. On one such throw, Charlotte throws the ball straight upward from the ground. The ball has no initial height when launched, and it passes the top of a flagpole when it is 6 meters off the ground. What is the kinetic energy of the ball when it is thrown upwards? Okay, well, let's draw a picture. Let's say we have our ground. We have Charlotte. They are throwing a ball upwards. We are saying that it is thrown straight up from the ground. So really it is launched all the way down here with a velocity upwards. And that velocity is 12 meters per second. As it passes the top of the flagpole, it is 6 meters off the ground. Okay, so we're saying it's going up, 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 up. If we have maybe our flagpole right here, the top being 6 meters off the ground. When it passes it, it is 6 meters off the ground, still moving upwards. What is the kinetic energy of the ball when it is thrown upwards? Well, kinetic energy, we have an equation for that. It is 1/2 the mass times the velocity squared. If we go ahead, we plug everything in, our mass, 0.2 kilograms. Our velocity is 12 meters per second. Don't forget to square it. Let's grab our calculator. If I can get it to work. There we go. Let's grab our calculator. We're going to do our squared first. 12 times 12, 144. Multiply by 0.2. Multiply by 0.5 for our 1/2. Kinetic energy, 14.4. Of course, we got to write our units. Joules of kinetic energy when the ball is thrown upwards. What is the ball's gravitational potential energy when it passes the top of the flagpole? Just asking about gravitational potential energy when it passes the top of the flagpole. We know the top of the flagpole is 6 meters high. Gravitational potential energy is mgh. We can plug everything in. The mass is still going to be our 0.2. G is 9.8 since we're on Earth. And the height is 6 meters for the top of the flagpole. We go ahead, plug in our 0.2, multiply by 9.8, and then multiply by 6. We get our answer. Let's get a decimal there. 11.76 joules. Okay. Let's even be consistent. Let's say we're going to round that to 11.8. Okay. Part C. What is the ball's kinetic energy as it passes the top of the flagpole? Here, we want to say energy is conserved, right? Total mechanical energy at one situation is equal to the total mechanical energy at another situation. Well, let's look at our two situations. Situation A here, on the ground, being launched upward. Situation B, at the flagpole, still moving up. At situation A, we have just kinetic energy. Situation B, we've gained some gravitational potential energy, lost some kinetic energy. But we have those two types. What we can do is say that at A, we have, again, like we just said, our kinetic energy. At B, we have kinetic energy and we have gravitational potential energy. If we take this, we write out our equation, we know the kinetic energy is 1/2 mv squared. And our gravitational potential energy is mgh. Go ahead, plug in all your information. We actually already calculated a lot of these. The kinetic energy at point A is right here. The gravitational potential energy at point B is right here. So if we go ahead, plug these in, we'd say that initial kinetic, again, it's 14.4. We still have our 1/2. Let's plug in our mass. It is 0.2. VB squared. mgh, the gravitational potential energy, when the ball is 6 meters into the air, is 11.8. If we go ahead, we subtract 11.8. We're trying to isolate for that velocity. This will cancel on our right-hand side, and we can get 14.4 minus 11.8. That gives us 2.6. So we have 2.6 is equal to 1/2 of 0.2 is just 0.1 VB squared. Next, we want to divide Divide both sides by 0.1, since it's currently being multiplied by our velocity, which we're trying to solve for. We want to undo that multiplication with division. 2.6 divided by 0.1 is going to give us 26. Is equal to the velocity of b squared. Take our square root, and we will get 5.1 meters per second for the velocity when it is passing a flagpole. Okay, so here I skipped ahead a little bit because I solved for the velocity, which is actually part D. But part C, all you have to do is this step that I'm highlighting right here. Right here, we solve for our kinetic energy, because really what we're doing is we're just taking the kinetic energy at point A, which we know, it's our 14.4. We're subtracting the gravitational potential energy, which we know, it's 11.8. Subtract those, whatever's remaining must be equal to our kinetic energy at point B. That answer is 2.6, and then if you go ahead and you set 2.6 equal to what you have left, that would be 2.6 for your kinetic energy is equal to 1/2 mv squared. You have the 1/2, the mass is 0.2, you're solving for the velocity squared, which is exactly what we did over here. So we get our answer. For D, the velocity is 5.1 meters per second. For C, the answer is KE equals 2.6 joules. All right.